Slava and Tom Kennedy. The plan for today is first I will do a small recap of RG blueprint, which Slava already presented in first week. Then I will give you a super short overview of what TNRG is. And then I will show our tools, our toys, which we developed, and show some results, intermediate results. Oh, sorry. So let's start with the blueprint. We work on with lattice systems. So we have some lattice lambda of size n. And let us imagine that there is some theory described by action. Then, as everyone knows what RG does, it takes theory on lattice lambda with coupling constants k, and it maps it to a new theory on a smaller lattice. And it maps it in such a way that partition function is preserved. So here b is just some integer, its scaling factor. Okay. So we want to study RG. We want to study some quantities using RG. And being on Bootstrap conference, I feel obliged to say that the most important quantities are quantities related to critical fixed points. And so what we want to talk about is a fixed point. So it should satisfy equation R k star equals k star. The only thing is that to start talk about this, we need to prove that this solution exists at all. And this is a question that bothers at least 3 people, gives purpose in life to 1 PhD student. And also I noticed that Sao Paulo is not indifferent to this question. You may see the signs of existence and not existence. But it hasn't yet decided what is the correct thing to give us. Okay, so we will focus on this equation. R k star equals k star. But we will try to write it in a little bit different formulation. We will talk about tensor networks. And well, let's just imagine that we already have a tensor network description of some lattice system. I may explain you how you can transfer your favorite lattice system to tensor networks maybe after the talk. But now we just have a tensor. It lives in some tensor product of Hilbert spaces. And then the partition function, it is described as a periodic contraction of these tensors. So each bond here means just taking a sum over some basis in V. And OK, typical RG step consists of, now it's a TNRG crash course right now. A typical RG step consists of 3 things. It consists of disentangling, coarse graining, and gauge fixing.
Just to be clear, this is in Euclidean signature?
Yes, everything is Euclidean. It's 2D classical StatMech. And today, I'm not going to talk about disentangling, and I'm not going to talk about gauge fixing because, well, disentangling is difficult, and I would need additional 10 minutes for this. Gauge fixing is too simple, so I throw it away as well. But we will talk about, I will show you how coarse graining works at least. But I would like at least give some grading to all these things so you would know what is a challenging part, what is not challenging part. And so for numerics, everything is simple. Simple, simple, simple. There is a gazillion of algorithms which can perform all of this. You can get quite good results. But in rigorous analysis, coarse graining is simple. Gauge fixing, we believe, is simple. We know how to do it in some particular circumstances, but now we're working on criticality, and we think we know how to do it, but it's not finished yet. So we think it is simple. Yeah, but you may guess that at least something's supposed to be hard, so yeah, disentangling is hard. So this table explains you why I'm going only to talk about coarse graining, because it's simple in all the regimes. Okay. So how coarse graining works? It's super simple. We just take this lattice, we divide it into pieces, and now we can just take 2x2 block. We can perform contractions. In a sense, we integrate out these degrees of freedom, and we get our coarse grained tensor. But then this is not yet. This is not it yet, because we would like to get, at the end of the procedure, we would like to get 4 like tensors. So we need also to define some isometry, so that it contracts into identity when you contract it like this, and apply it to the legs of coarse grained tensor. And this is a coarse graining, very, very simple thing. The only problem with coarse graining that, well, what we would expect to see. For example, for Ising model, we expect that we have some Ising line here. We have critical temperature, and flow should look like this. It should flow to high temperature fixed point when we are above critical temperature, to low temperature fixed point when below, and so on. Well, if you just take coarse graining and you run RG on a computer, well, you will see something like this. It doesn't converge at all to the places we would like it to converge. But if you add disentangling and gauge fixing, all these problems disappear. But as I said, we don't have a lot of time to discuss disentangling. Okay, yeah. This is just RG step. Yeah. Good. Okay. This was a crash course. I hope at least now you may imagine what is going on during RG. And yeah, now let us focus on this equation. R of A equals A. Let me write it down. So this is our holy grail. This is what we want to solve at the end. And well, how can we do it? Let us imagine that we already know where the fixed point is. And then we understand the flow, at least in a small neighborhood of this fixed point. It's, for example, for Ising, we should have irrelevant directions, relevant direction. The flow should be like this. And so imagine we located this neighborhood. Maybe we don't know the position of A star, but we have this neighborhood. Then what we can do is we can define the Newton map. N of A looks like this. And it has two good properties. First is being a fixed point for N of A is the same as being a fixed point for R. And second, if you compute Jacobian of N at A star, imagining that you have this A star, then this Jacobian is 0. So the flow around A star, if we use N for generating the flow, it should be very simple. It should just everything should flow to A star. Okay. There is a problem, however. that this map, more often than not, it doesn't exist. Why? So the thing is that we need to invert this matrix here. And well, we know that R of R corresponds to dilatation operator if you talk about the fixed point, right? And we know how spectrum of Jacobian of R at the fixed point should be related to CFT spectrum. We know that lambda I is supposed to be B, D minus delta I. And so unfortunately, we have stress energy tensor. Well, maybe fortunately, but stress energy tensor has a dimension exactly D, and we get eigenvalues 1, which is a problem, because now we cannot invert this thing. And what we came up with in one of the papers I showed in the beginning is that we can do a very easy thing. We can take our R, and we can define new RG map, which would be a composition of rotation with R. And now it's no longer a dilatation operator. Now it's composition of rotation and dilatation operator. So this formula is modified with the spin-off operators. And this removes this nasty eigenvalues 1 from the spectrum. And now all of a sudden we can run the Newton map. Yeah, I should have showed it, but well, yeah, I think you know how the spectrum of Ising, for example, is supposed to look like. So you see here we have this minus ones, we cannot have Newton map. Now we added rotation and we have it. Another small simplification, which I think will be very useful for us in the future when we will manage to prove the existence of the fixed point, is that we can replace all this thing with just approximation of the Jacobian, and it will still work. And we checked it numerically. It works beautifully. We got the fixed point to the precision 10 to the minus 9, which is the best precision anyone ever had. Well, OK. It's good, but all this only advanced us in numerical sense. Well, we unlocked Newton map. We can use it in our proof at the end. It will be a very, very nice tool. But for now, we only have this numerical result. And numerical fixed point is not yet what we want. And yeah, and how are we going to really tackle the problem of existence of the critical fixed point? There is a nice mathematical theorem which can help us with this. I think I should write it here. So it's called the Earl-Hamilton theorem. And it goes as follows. If you have some Banach space X, and you have some subset, which is supposed to be open and bounded, and you have some map, which is going to be our Newton map at the end, which acts from E to E, and such that f of E is strictly inside E. Strictly inside means that there is some epsilon gap between this image and complement of E. Then iterating F, we should get to fixed point. Oh yeah, I forgot to mention that F also must be analytic. So what this means in practice, it means that now all we need to do is to have some analytical RG map, which is usually what we have when we try to work not with numerics. And what we need to do is we need to find some neighborhood such that it maps into itself under this Newton map. And then we won, that's it. Okay, but how? How can we do this? It still looks very non-trivial because we work with infinite dimensional tensors. We need somehow to construct this, this neighborhood.
Sorry, what does analytic mean on Banach space?
Yeah, you may just think about it as if you have convergent power series at every point of your domain. Or it's just differentiable, it works as well.
Power series then means like continuous multilinear form?
Yes, yes. Okay, so how are we going to do this? And this is our second tool. Which I will explain talking about high temperature fixed point, just because it's easier. But we think that it's supposed to be possible. We're quite sure it's possible to use it at criticality as well. At least we don't have any other tool to do it. Okay.
Sorry, I'm a bit confused by the statement.
Sorry?
I'm a bit confused by the is Fn the n iteration of f?
Yes, it's nth iteration of f.
But then, like, say I take a map that rotates in the plane.
Your image should be strictly inside. It means that you should have some distance here.
So, sorry, you're saying it's a contraction? Or?
Well, I'm saying that it should map its domain strictly inside itself.
But it maps, so take a disk, a rotation maps the disk.
It's not strictly inside. Strictly inside means you say you take disk and you get disk back, but you don't want to get disk back. You want to get something smaller.
No, but the oven interior of the disk is mapped in the. Anyway, yeah. Okay, maybe I'm missing what strictly inside means. But, so you're saying that.
Huh?
You mean that the closure needs to be inside, or?
No, just the image should be strictly inside.
Oh, but then rotation of the disk, yes, it's.
No, it doesn't work because if you rotate disk, it's not strictly inside. Let me write down what strictly inside mean. Maybe it will help. So it means that distance between f of E and E.
Inverse complement.
Complement, yes. Good. Okay.
But then that's at least saying that the closure is inside.
I don't think it's true, because you can have something. You can have situation like this when when your interior touches the. Okay. Okay. Yeah. I guess then the closure inside it's fine. Yes, you're right. Okay. So how are we going to do this? Okay. Let me just have this picture here so we remember what we want to get. But we will talk about simpler problem. Let us think about the flow near high temperature fixed point. So it is quite well understood. Slava and Tom written the paper which explains that this fixed point is a stable fixed point and so on. So we know that it looks like this. This is a flow under just RG map. We don't even need to use Newton map here. But what was hard with the techniques in this Slava's and Tom work is that it was quite impossible to get the size of the region that flows to the fixed point. So size. And also, even if you would manage to do this, which is possible, you should just go through all the proof, you should collect all the constants. I'm quite sure the size would be just some minuscule number. But we would like to have a technique which would get us a big box. And so And so it seems like we came up with such a technique which allows to analyze the flow quite well. And for this, I need to introduce an old thing. It's called head tensor. Or you can think it's some bounding box. We still need to fix our notation. And so how it works? Well, first of all, what is high temperature fixed point? I think it will be nice to understand this. So AHT is just a tensor with only one tensor element. All indices are 0, and this tensor element is 1. And now we are interested in deviations away from AHT. So we look at AHT plus some small b. And b, it again lives in the same space indeed. V times V times V. Good. Let us now do the following thing. Let us take V and decompose it into two subspaces. There will be subspace O and subspace X. And subspace O is just a span of E0, exactly the same 0 as in definition of high temperature fixed point, and X is the rest. Okay. And now let me introduce a small piece of notation. When I write I, J, K, L, these are just numbers. And so these are indices of tensors. And when I write A, B, C, D, these are things which are either O or X. So they denote these sectors we divided our space into. And then when I write, for example, B, A, B, C, D, this is a tensor which just lives in A times B times C times D. So it's a projector of my original B on this subspace. Okay. Okay. And then we define head tensor as follows. We define this B head. It lives in R2 times R2 times R2 times R2. And in each R2, our basis is EO and EX. So we label the basis with these subspaces now. And the definition, we say that B head is a head tensor for B if, well, I think it can have better place. Okay. If the norm of B, A, B, C, D is smaller than B hat A, B, C, D. Okay? So we divide our space on chunks. We measure norms of our tensor in these chunks, and we bound these norms with this B hat. And this is quite a nice tool because there is a lot of operations with tensors which are head friendly. So for example, if you try to contract two tensors, B1, B2, and we want to compute a head tensor for this thing, then we can just contract two head tensors. And this just works. Then we can take sums. With slight generalization of this definition, we can even multiply by arbitrary constants and subtract tensors from each other. So it's a nice thing. And okay, then if we have, imagine that we have some RG map R that consists only of head-friendly operations. So we use only something which we know how to estimate using these heads. Okay, then we can define what we call master function for now. That if you have R of B, yeah, now I write R of B because we are around high temperature fixed point instead of R of A. And we want to evaluate its head. then we have actually a master function that we should just apply to be head. Okay? And it means that we now can track the flow of the tensors in finite dimensional space using these bounding boxes. We can just, instead of iterating R, we will iterate master function, and it will give us the flow. Okay. And this is how this flow looks like. Here I have a bit more labels than just O and X. It's just a technical minor detail, but this U, R, D are just the same. We just subdivided a little bit to a finer precision. And what is nice on this picture is, first of all, you see this chaotic part, completely chaotic part. And it already tells us that we have some sort of a control over the flow in the regime where it's very much nonlinear. Another thing about this plot is that we can use it to prove that high temperature fixed point is stable again. How can we do it? We can just look at this step 15, for example. We can compare it with step 16. We see that all the lines went down, which means that this bounding box, it shrinked to a smaller one. Then we can use Earl Hamilton to conclude that we have a fixed point inside. Good. Okay.
Is M obviously unique?
M, no, head tensor is not unique in general. You see this definition is just an inequality. So yeah, but you just try as best as you can to get as good approximation as you can. And it's, what is nice is that it's very simple to construct at least some M. If your map is described using some diagrams, you just put heads everywhere and it works, which is very useful. So yes, this is more or less the answer on how question. We hope that we can use these head tensors, analyze their flow near criticality, and if you show that they shrink, then we won. Okay. So first thing is we unlocked, as a summary, we unlocked the Newton method, which is great. We have a map to analyze. We have this new concept of head tensors, which we can put inside the computer and work with them. We can also sprinkle it with the interval arithmetics, and everything becomes completely rigorous. And also think I didn't mention, actually, already now we have compute some simple observables. Well, some people in our collaboration think that it's uninspiring, but I still would like to show it because I think it's nice, because such pictures never were produced using RG. What you see here is just free energy for Ising, depending on temperature. And this red line is exact result, and blue lines are our RG computation, and these are exact error bars, so we know for sure that it's supposed to be here, and we can crank up the dimension and get better result, and so it's improvable approximation, which is great. Even though for this picture I used just coarse graining, so it's but you can use it for such a computation. It's okay that it doesn't converge to the fixed point.
Sorry, can you say again, what is the quantity again?
It's free energy, density of free energy.
In what exact system? Like,
Ising,
exact
just
result.
nearest neighbors Ising.
When you say exact result, what is the meaning of this? Is this
Well, you have an Anzeiger solution, and you have exact result.
and so, in what sense does your RG computation tell you what the free energy is for ETC, TRC equals 0.6? Why do you need RG for this?
Well, are you sure you want to ask why I need it, or?
Well, you were talking about fixed points, right?
Yeah.
And now you're telling me like free energy in a lattice model.
Yeah. I mean, sorry, maybe I didn't emphasize it enough. It's just a cherry on cake for me. I like the fact that we can compute some physical properties of the system with rigorous error bars.
I like that you like it. I just don't understand how it's connected to anything you're saying.
Basically it's connected only to this head tensors idea, because we can do this only because we invented this thing. We invented things that can track down all the errors, and we can produce rigorous error bars in computations. Yeah, I can give a formula. You mean you want to? Oh, yeah.
Trying to understand the logic. We're discussing just one tensor, right? And you're only concerned with fixed points.
Yeah, it's a jump in the logic, I see. It's not logical, yes.
Very particular lattice system with all its,
Yeah.
unique details and computing the free energy in that system.
Yeah, sorry for this jump. Yeah, it was not very logical, I agree.
So somehow this technology just you can, so do you take like lattice system and code it in your?
You encode it in tensor networks, then you run RG, and you can use it to compute stuff. Yeah.
So you run RG, that means that.
Yeah.
Like, does this for you become like a way of doing thermodynamic limit essentially? Or?
You may think so if you wish. Yeah.
I'm just not.
Yeah. Sorry. Maybe it was just too much of a logic jump to show these plots.
But maybe on a related note. So
Yeah.
Does your method work also away from the critical point?
Yeah.
Because like the way at the beginning the blueprint was for critical points, right?
Yeah, we wanted to solve critical
But now
point.
you
Yes.
show results also away from criticality. So
Yeah, it was stupid to show it.
no,
I
it's-
see. Yeah, just forget all the talk about criticality and focus on the existence of this cute toy that we have now, which allows you to track all the errors in RG flow. And now you can use it for something else, not only for trying to prove existence of critical point. Yeah. Okay. Thank you for your attention.
The examples were in the Ising model, but this applies much more generally.
Yeah, you can do whatever. As far as your, say you would like to be on a lattice, and you would like your degrees of freedom to live in something compact, because otherwise it would be hard to rewrite it as a tensor network. At least I don't know how to do this. Good.
Are there any questions now that we have the mic?
So, for example, gauge theories on the lattice would be hard. I don't know if it's on.
It's just, yeah, it's for YouTube.
Oh, I see. Thanks.
Gauge theories would be hard.
But you can have emergent.
Because you'd have an infinite number of degrees of freedom per site.
I have infinite number of discrete degrees of freedom. This is fine.
That's
is
fine.
Yes.
Okay.
Yes, as I said, as long as your degree of freedom lives on something compact,
I understand.
you can do some sort of Fourier or whatever, and it's fine. Yeah.
Okay.
So I think you can do gauge theories.
Okay. Okay. Yeah. Thank you.
Maybe one small question. So this analytic condition is just trivially satisfied because you're in a finite dimensional vector space.
We are
and
not in
some-
finite
or-
dimensional vector space.
No, you're not. Okay, so
Yeah.
then why do you know that this analytic condition is?
It's on us. We need to construct an RG step which is analytic.
I see.
You need to search for it, yes.
Can you comment on the importance of dimensionality? So 2D versus 3D, how much more difficult it is?
Yes, so disentangling is already hard in 2D. It's even harder in 3D. Even numerically, it's hard. Becomes even numerically hard. Yes. Thank you.